Hey y'all, we're going to start a new unit now on functions. Now really, in the last unit when we were doing linear equations, we were really doing linear functions at the same time. So we've done a little bit of work with functions already, but we're really going to get into some new material now with looking at functions and then specifically looking at exponential and quadratic functions because that's a huge part of what we have to do for our state test. So we're going to kind of go into that and then after that really start preparing to review everything that we need for our state test. So by the end of this, you should be able to identify functions, which this will be review for anybody who had me for foundations. We did this. Now what we start Wednesday will be new stuff for you, but we did do identifying functions and describing their characteristics. So some of this will be new. If you didn't have me for foundations, then the identifying functions is something you did in 8th grade, but describing these characteristics may be new for you. So some of this will be new, some of it won't. None of it in this lesson is particularly difficult. So hopefully you'll feel the same way about it once we get done. So let's go. All right, so let's start by talking about what a function actually is. So a function is a mathematical relationship where one input has exactly one output. That means that if you put a number in the function, that you're going to get a number out of the function. And that if you put that same number back into the function again, you'll always get that same output back out. There's no way to get two different outputs from the same input. So one input has exactly one output. Functions can be represented by a variety of things. We look at them on graphs. We see them in tables. We see them in equations. And we see them in diagrams. So there are really 6 different types of functions that we look at in Algebra 1. 3 of them we focus heavily on, and then the other 3 we just kind of look at a little bit. But I want you to be familiar with all 6 of them because they are going to come up at different points in time. So the one that we're most familiar with is linear. That's what we just finished. And we know linear functions are ones that look like a line, right? So it can be rise and fall and whatever, but it's going to look like a line. Then we have exponential functions. That's where we're going next. Those are these L-shaped functions. They kind of look like that. Quadratic functions will be the last major area we study in algebra. And that's going to be our U-shaped functions, this parabola-shaped. And then we'll look a little bit at absolute value and square root and piecewise functions. Absolute value functions are V-shaped. Square root functions look like half of a quadratic turned sideways. They're not a full letter at all. And then piecewise functions are like little bits and pieces of different ones put together. So you might have a section of a linear function that is then accompanied by another piece of something linear and then something exponential or quadratic kind of tagged onto the end. So different pieces of different functions put together in a piecewise function. A lot of times those piecewise functions are just chunks of different linear functions put together, but not always. All right, so let's look at what we want to be able to tell about functions. So we need to be able to tell if something is or is not a function. That's one of the standards for algebra. And you've done this in 8th grade, and we did this in foundations, and now we're here doing this again for Algebra 1. So this should all be review for you for the most part. But the way we look at a graph and tell if a graph is going to be a function or not is by using the vertical line test. And so the vertical line test basically means you're going to draw a vertical line through the function. And if it is possible for that line to touch that function more than once, then automatically you know it is not a function. So what I mean by that is if I were to take a line like this one, Let's see if it'll let me pick it up, because that'd be great. Yeah, it will. Just kidding. All right. If I took this line right here and I went through this function, right now where I've placed it is only touching the function one time, right here. If I continue picking it up and moving it, everywhere I move it to, no matter where I'm at on the line, it's still only ever touching the line once. That means that line represents a function. Now, if I go on this line, if I touch right here, I'm only touching once. But if I get anywhere else in this graph, like if I'm right there, for example, I'm touching that twice. I'm touching here and I'm touching here. So because it would touch it twice, this is not a function. So that's how the vertical line tests work. If it touches once, it is. If it touches more than once, it is not. All right, now let's look at how to look and see if a set or a table is a function. So when we look at that, we're going to look at the x values only, because those are your input values. And remember, your x's are the ones in the top row or in the left column of your table. And you're going to, or if you're looking at ordered pair, the one in the first position in an ordered pair. So you look at only those numbers, and your goal is to figure out whether those numbers repeat or not, because if they repeat, that means they're used more than once, and it's no longer a one-to-one situation. So if any of the x values repeat, or the input values repeat, it is not a function. So when we analyze these, we're only going to look at the x's, only looking at inputs. So I'm looking at inputs, I'm looking at inputs. Over here, when I'm looking, I'm going to be looking just at the x values in each ordered pair. And if any of them repeat, meaning the same number is there twice, it is automatically not a function. So when I look at this first table, 2, 5, 8, 2. 2 is in there twice, not a function. 0, 1, 2, 3. They're all different. This is a function. 2, negative 1, 0, 1. They're all different. This is a function. 7, 9, 7, 12, 15. 7 is in there twice. This is not. So that's really easy to be able to tell. And then we got to be able to look at an equation to tell if it's a function. So if you're going to look to see if an equation is a function, I just want you to graph it. And then do the vertical line test. That's your easiest option. And when I made these notes, just before we had used Desmos before, these are from last semester, and I kind of adjusted them, but I forgot to take this out. So, of course, if you're graphing an equation in Desmos, you just type it in. Make sure you use x and y for your variables. It's not going to recognize anything else, so you've got to do x and y, even if they don't use x and y in the actual function. But if we're going to do that, so I'll pull this up, and we'll look at an example of it. So if I wanted to graph this first one, x squared plus y squared equals 9. When you look at the graph of that graph creates a circle. So I would do vertical line test on this circle to see if it is or is not a function. And I know that if I drew a line through this, it would touch twice. So this is not. Now if I do y equals x minus 3, which is the next one, and I know that's going to be a function because it's linear. And mx plus b is always going to be a function. But if I look at that one is a function because it's a straight line. And if I put my vertical line on that anywhere, it would only ever be able to touch it once at a time. So this is a function. The other one is not. Now there are some things that have exponents that will be functions. So you want to make sure that you're not just assuming if it's got an exponent in it, it's not a function, because there are a lot that are. So graph it in Desmos and then do your vertical line test on it to be able to check it. Oops, just kidding. I was trying to get rid of that. X. There we go. And this says line. I realize that's not very clear. Vertical line All right, so here are a few that I want you to try. So try the ones on this slide, and then actually try the ones on the next 3 slides. But there are a couple that have function diagrams on them. In those ones with function diagrams, just know that the letter on the circle on the left represents your x's. So take a few minutes, work through those, and see if you can figure out whether they are or are not functions. You can just label them with an F if they are and an N if they're not. On these ones that are just dots, don't connect the dots. Look at the dots where they stand and see whether you think that's a function or not based on where those dots are. Don't draw extra lines that are not already a part of that. Okay, pause the video, try all of these out. So this slide and the next 2, and then come back and see if you were right. Okay, so looking at these, now that you've taken some time to work them, so you should have gotten the first one as a function. There are no 2 dots that are going to touch the same line at the same time. So first one is a function. This one, though, was not because of these 2 dots. They together would touch that vertical line both at the same time, so that made it not. This set here was not a function because we've got repeat of the 3's and repeat of the negative 2's. But this one was a function because none of those x values repeated there. And then the next one, on these input diagrams, input-output diagrams, this one was a function because each input gets used 1 time. 1 matches up here, 3 matches up here, 5 matches up here, 7 matches up here. This one was not because the input of 0 gets used twice. That means 0 would exist 2 times in our set, and that can't happen. This table was a function because all the inputs are different. This one was not because 1 repeats and 4 repeats. And then you got into these graphs where you did your vertical line test. So this one was not because it touched twice here. This one was not because it could touch 2 or 3 times really through this section here. This was a function because this line exists here and a line would only cross once. A vertical line is never a function. So this line would touch everywhere, which is why that's not a function. Every single point on this line would touch. And so this one is not a function too because it has a piece of a vertical line in it. And this was a function because it only could cross once anywhere you drew a line there. All right, hopefully you got all of those correct. If you didn't, take some time to make corrections where you need to, and then let's move on. All right, so in addition to needing to be able to tell whether something is or is not a function, there are certain things I need you to be able to describe about functions. And probably the most important of those is domain and range. So when they ask you to talk about the domain of the function, they're asking you to describe all the x values in the function. If it's a function, those values will not repeat. Now when they ask you to talk about the range of the function, they're asking you to talk about all the possible y values. And remember, it doesn't matter if those repeat or not. So anytime you hear that word domain, you need to think x. Anytime you hear the word range, you need to think y. This is no longer like the range where you subtract the big and the small number. This is describing a function's range, looking at how low and how high it can go along the y-axis. All right, last semester when we learned about functions, those of you who were in foundations anyway, we looked at how to do domain and range, and we used 2 different kinds of notation. We used set notation, which used inequality symbols, and we used interval notation, which used like brackets and parentheses and things like that. I have since looked at some of that a little more closely and realized that nowhere on your state test are they going to put things in interval notation. They're only going to do set notation. So while it might have been useful for Miss Smith for us to go ahead and do interval notation for algebra, she can teach you that when she teaches it to you in Algebra 2 and be fine that way. So we're not going to spend any time really looking at interval notation this semester, although some of you have already seen a little bit of it. We're going to focus strictly on set notation and understanding what set notation is asking us to look at, because that's what you're really going to see when you take your state test with this. So set notation uses a couple of things. You're either going to have a list of numbers, or a mathematical statement with inequality symbols. misspell, y'all. Statement. So it's either going to have less than or less than or equal to. You're really going to have those two symbols to define possible values of the x or y. If you're using a list, the numbers must be in order from least to greatest. And they must be surrounded by these curly brackets, which I'm terrible at drawing, but you know the little curly brackets, not the box brackets, but the little ones that look kind of like that. Do better to just type them, probably. The brackets that look like this. Those kind of brackets. All right. Anyway, I can't make that bigger. Anyway, so those kind of brackets. Other things I want you to be able to describe about functions are maximum or minimum. So if they have a range that is not infinite, then there's a chance there's going to be a maximum or a minimum, depending on if there's a highest point or a lowest point on your y. Now, if you have multiple points that are highest or lowest, then you don't call that a maximum or a minimum. But if there's one single point that is the highest or one single point that's the lowest, and you usually see that in those U-shaped graphs, those parabola-shaped graphs, where there might be a high point or a low point on that, then those are the ones that you're going to see a maximum or a minimum. So if you're asked a question about that, that's what they're looking for, that highest point or that lowest point along the y-axis. Then you also have to be able to identify x and y intercepts. And I know you already know how to do that or know what those are. But I added this extra word in here that says zeros. And that's going to be important to you because an x-intercept and a zero are the same thing. So if a question asks you identify the zeros, all you got to do is find where it touches your x-axis. So know the word zeros. Be able to identify the zeros from the graph by knowing the x-intercepts. Y-intercepts, of course, where the function touches the y-axis. There's no special word for that. And then the other thing you need to be able to describe is the behavior of the graph. So the graph could be doing one of three things. It could be increasing, and that means it's rising from left to right. It could be decreasing, which means it's falling from left to right. Or it could be constant, which means it remains horizontal or flat. That behavior is always described across specific intervals, and those intervals are described by the position of the function on the x-axis. All right, let's look at some examples of all of this then. So here we've got a graph of a function, and they're asking us to describe its domain, its range, its maximum or minimum, x and y intercepts are the zeros, and the behavior of this graph. So to start with domain, when you think about domain, you need to be thinking about along your y-axis, your x-axis, how far left and how far right does this function go? Now, it doesn't have to be the actual points on the axis. It's not this point and this point, because the function has points that are further left than that spot where it touches. So when I think about this function right here, and I think about how far left does it go, right here it's at -3, but there's an arrow there which tells me that this would keep going this direction, which means eventually it would stretch out as far as -4. And eventually it would stretch out as far as -5 and -6 and so on. So this arrow on the end of this and the fact that it's getting wider up until that point tells me that this is going to infinitely get wider to the left. So infinitely bigger towards the negative side, which means it approaches negative infinity in this direction. And now when I look at the other side of it, it basically does the same thing, but towards positive, because it's at 3 here. But if I kept going where that arrow tells me, I eventually would be lined up with 4. And eventually I'd be lined up with where 5 would be, and so on. So the domain for this function is going to be from negative infinity to infinity. And so the way that we show that is we put an x in the middle with less than symbols on either side. And we put infinity on one side, or negative infinity on one side and infinity on the other. Always start with your smaller value. Now, you might also see this written as all real numbers. But x would be between negative infinity and positive infinity. We don't use equal to bars on this because you can't actually reach infinity. So x will never equal infinity. It'll always be in between negative infinity and positive infinity. Now, when we think about range, we need to think about along our y-axis. How high and how low does this function go? So my y will go in the middle of my interval. The lowest number goes on the left side. The higher number goes on the right. So when I look at how low this function goes, right now my lowest point is at like -4. Because this or this indicate that I'm at -4 down here along the y-axis. But I know that those arrows tell me this keeps going down forever, which means the lowest this would ever go is negative infinity. Now I'm going to look at how high the function can go. So on the high end of the y-axis, the highest this function ever reaches is 2. Because once it reaches 2, it then turns around and goes back down again. So 2 is my highest value. So the upper part of my range is 2. Since that's a number on the line, I'm going to use the equal to bar for that one. So the range is where y would be greater than or equal to 2. Now this function has a maximum because it has a highest point. It has a maximum. That maximum exists right here at 2. It also has 2 x-intercepts, or zeros. 2 places where it touches our x-axis. And that's here and here. So our 2 x-intercepts, or our 2 zeros, are -1, 0, and +1, 0. And then we have one place where it touches our y-axis. And we can see that right here. And so my y-intercept is 0, 2. And then we'll look at our behavior. So this graph is doing 2 things. If you start on the left side of it, and you were going up the graph, if you were riding a bike, you would be riding uphill. And then once you reach the top, you would then be going back downhill again. So this graph is increasing, and then it is decreasing. So I'm going to describe both behaviors. It's increasing and decreasing. So to describe where it's doing what, I've got to describe it according to where it is on my x. So it starts increasing from the very beginning, right? So over here, from here to here, it's increasing, which means if this graph kept going, it would be increasing still from that point as well. So it starts increasing at negative infinity. It stops increasing once it hits this point right here. Now, y'all might say, well, it stops increasing at 2. That's the value on the y. On the x, it's at 0, right? So where the x is 0 is where that turning point is. So from negative infinity to 0. And then it begins decreasing after that. So it starts decreasing at 0, and it stops decreasing never. So it continues to decrease infinitely. So to infinity there. It gets a little tricky to write those intervals. Good thing about on your state test is they're not going to ask you to write an interval. They'll give you the interval, and you just have to understand what that means here. So when you look at this interval here, if they gave you that, you would have to know to look at anywhere that x was less than 0. So from 0, anything on this side. And of course, that piece of graph is increasing in that section, because if we read it from left to right, we would be riding the bike up the hill. All right, keep going. Up until that point. Now this is called, or this is a different kind of graph. This is a discrete graph. The other was continuous. So continuous data is connected with lines. Discrete data is just points. So when you have discrete data, you have to do your domain and range as a list of points. It cannot be an interval, because there's not anything in between it. So the easiest way to come up with your points for that is just to actually write your ordered pairs down. Like this is located at 1, 4. This is at 2, 5. This is at 4, 1. This is at 5, 3. So to give our domain and our range for discrete data like this, we just list our numbers out using those curly brackets, making sure to list them in order from least to greatest. So the domain of this would be 1, 2, 4, 5, because that's the x values from least to greatest. The range of this would be my y values, again, from least to greatest. So my y's are 1, 3, 4, 5. Now, if you have discrete data like this, you don't have a maximum or minimum unless your data fits a particular pattern. But typically, there's not going to be a maximum or minimum. You could have x and y intercepts, but you don't have to have those. And looking at these, none of the points fall on the x-axis or the y-axis, so there's none of that either. And unless your data follows a particular pattern, you can't describe its behavior either. It's just individual points. So we have no way to describe behavior for this one either. But you do need to be able to give domain and range for something like that, something that's just points. You don't give an interval, you give individual parts of that. All right, let's keep going. Now here we have back to another continuous one, because we've got the line that connects it all. But this one's a little bit different than the first one we did, because there are no arrows on the ends of our line segments here, which means that we're not going to have anything that goes infinitely in any direction. So when we look at the domain of this, and I want to describe where my x's are, I've got to think what my boundaries are for where this touches our x. So when I look at this, the furthest to the left my x value ever is in this point right here, which is at 0, I'm sorry. And then my furthest to the right my x ever is at this point right here, which is at that 1.725. So my domain for this tells me my x is going to be between and equal to, because the points are here, 0 and 1.725. And I'm going to go and do the same thing with my range. So with my range, I need to look at what's my lowest value. So my lowest point vertically is this point down here. My highest point is this point right here. So the range for this, and that's my y, is going to fall between 0, because my lowest point down here is at 0 on the y, up to this point here, which is at 24. Now this graph does have a maximum. It has a highest point at 24. It also has an x-intercept. It touches my x-axis one time right here at 1.725, 0. It also has a y-intercept at this point right here, 0, 20. And we can describe the behavior of this graph as well, because this graph is increasing to begin with, and then it starts to decrease after that. And so we'll describe both behaviors along their particular intervals. So it's increasing and then it's decreasing. It increases, remember we're describing this from where it is on the x. So from 0 until it reaches this point right here. So this point on my x-axis is at 0.5, right? 0.5, and it gives me that point. So it increases from 0 to 0.5, and then it begins to decrease from 0.5 until it stops altogether at 1.725. When you're describing the behavior of your graph, if you describe everything, you should have the beginning of your interval for domain and the end of your interval for domain as the beginning of your first interval and the end of your last interval when you're describing its behavior. Okay. We'll do one more together and then let y'all try some of these. So here we have an exponential function. This is what we're going to get into starting Wednesday. But those are these L-shaped looking graphs here. So they have arrows on both ends, which means it's very possible that we'll have an infinite answer on some of what we have here. But we'll start with domain and range. And so it's always going to set up like that. Domain for this, if you look at how far left or right it goes, this is my leftmost point, but I have an arrow there which tells me this would keep going this way forever. And this is my rightmost point, but I have an arrow here telling me it's going to continue to go up and then still get further out, because notice how it's still getting further outward as well, forever, which means that my domain is going to go from negative infinity to infinity. And that's going to be true about most of our functions. Now, you could also call that all real numbers. Now, my range, though, is not going to be infinite in both directions. And the reason that it's not is that this point down here, you can see where this curves and makes this tight curve. And while you might say, well, it's getting closer and closer, eventually it's going to cross, it actually is not. And that's the whole idea behind an exponential function, is there's a limit line right here that it's not able to cross that. So it'll keep trying to get closer and closer to it, but it never actually touch it. So the range for this goes as low as 0, never actually touches 0, but goes that low. And then it continues to go higher on this side forever. It will go up forever, but it will not be able to go down forever. It has that limit, that stop. So from 0 to infinity. Exponential functions do not have a maximum or a minimum. They also typically, unless they've been transformed, don't have an x-intercept. They're not going to touch your x-axis. So there's actually no x-intercept either. The y-intercept, though, will exist almost always, and that is going to exist at 0, 1. And then exponential functions will only have one behavior. They'll either be increasing or they'll be decreasing. There's no multiple behaviors to an exponential. So this one in particular is increasing the whole time, because if we start on the left, we would be going up always. So it is increasing. And since it's always increasing, it's increasing where x is from negative infinity to infinity. So I'd like you to pause the video and try this one and the next one. Write your domain and range, decide if there's a maximum or minimum, and describe it if there is. And describe your intercepts and the behavior of your graph. Then when you've finished all that, come back and see if you got correct answers for both. Do this one and the next one. All right, hopefully you've taken some time to work through these and are ready to check. So I've got my answers written in here. I've got my domain to be from negative infinity to infinity because it continues to go wider in both directions, left or right. Range went from negative infinity because it goes low forever up to 0 as the highest possible point. We had a maximum right here at 0. X and Y intercepts were also both right there at 0, 0. And then it was increasing from negative infinity until it hit 0, and then it began to decrease from 0 on to infinity again. So I describe my behavior as increasing and decreasing on those intervals there. And then on the next one, Its domain went from 0 across to 90. That was the furthest left and right it went. The range was from 0 up to 30,000. There was no maximum. You might have thought this was a maximum, but it's multiple points here, so we don't call that a maximum. It's only a maximum if it's 1. So no maximum. There were 2 x-intercepts, one at 0, 0, and one at 90, 0, and a y-intercept at 0, 0. And then this was actually increasing, constant, and then decreasing. And so I've got a increasing from 0 up to 30, because that's where my x would have been right there. And then between 30 and 60 on the x, it was constant. And then from 60 down to 90, or from 60 to 90, it was decreasing. So we've got increasing, constant, and decreasing there. All right, make corrections if you need to. Otherwise, we'll roll on. So then this is how this is going to be tested. So you've got a question like this one where they give you some numbers and a table, and they ask you to figure out what you could put in place of x to make this a function. Now we know the only thing that keeps something from being a function is for one of those input values to repeat itself. So as long as we don't repeat anything else from here, we should have something that would create a function. So unless I pick -7, -3, 2, or 5, anything else could go in this space and keep this as a function. So -3 is already up there, so if I put it, it would be not a function. -2 is not up there, so adding it would be fine. 1 is not up there, so adding it would be fine. 2 is already up there, so we can't use it again. 3 is not up there, so it would be acceptable too. So if you're looking at one like that where they're asking what you can put in that space, just make sure you don't let anything repeat, and you should be okay. All right, then you have this one that asks you about the function that's over here. They ask you to choose 3, and that's really how they have your state test, created your state test, is they give you a specific number of answers to choose. So when you look at these, you want to limit yourself to only that many choices. Make sure you pick that many, because if they tell you choose 3, there's 3 that are correct. So this says, A says the function increases for all real numbers. Well, looking at this, we know it doesn't increase at all numbers because it increases here, but then it decreases again. So it can't be A. B says it decreases for all real numbers. Well, we know that's not true either. So now we've got questions about where it's increasing or where it's decreasing. And so they say it's increasing on the interval from 0 to 0.38. So I'm going to look at that interval and decide whether I think it is or is not. So at 0, I'm here. At 0.38, I would be right in front of the 4, which is right here. So on that interval, is it increasing? Absolutely it is. That section of graph is increasing. So this is true. This says it's increasing from 0 to 8.3. Well, I don't even count to 8.3 on my x-axis, but I know good and well that once I get past this 0.38, it starts to decrease again. So that's not true. E says it's increasing from 6 to 8.3. Again, I don't even see that information here, but from what I can tell on this, it would be decreasing still at that point if we could extend this graph all the way out. So then F, obviously it must be F and G, but let's look at why those are true. So F says it's decreasing from 0.39 to 0.76. So 0.39 would be right here, 0.76 would be about here. That goes from this to this. That section of graph definitely decreasing. So this is acceptable. And then the next one says from 0.76 to 1.1. Well, if 0.76 is here and 1.1 is here, that section of graph is also decreasing. So that's true too. All right. Created. And then this last question. So they give us a graph of this, but they say the function f of p equals 45 minus 4p represents the amount of money in dollars Jim has after purchasing p packs of trading cards. The function is modeled by the graph. And so we can see in this graph that it starts at 45 and it decreases as time goes on as he's purchasing more packets of trading cards. And our questions ask us about the domain. So remember, domain is your x value. So in this, your x's represent your packs of trading cards. So when you think about your domain, think about what makes sense in terms of packs of trading cards you could buy. So A says the domain includes all real numbers. All real numbers includes everything positive and negative. And we know it's not possible for him to buy negative packs of trading cards. So A is out. B says the domain of the function includes all real numbers where P is less than or equal to 45. That means that all real numbers, anything less than 45, that also includes your positive and negative numbers. Negative numbers can't be included, so that's out. C says the domain includes all whole numbers where P is greater than or equal to 0. Now, that might be reasonable because you can only buy whole number packets, and we can only buy things that are positive or buy none at all. So let's not discount this yet, but let's look at the next one. This one says the domain includes all whole numbers where P is between 0 and 11. So here we have whole numbers again, which makes sense, but this gives us a limit. C says anything bigger than 0 is fine. D says from 0 to 11. And so we've got to decide which of those is reasonable for this. Now, obviously, this function is decreasing, which means eventually he runs out of money. So it's not feasible or it's not reasonable to say that he could go forever and buy as many playing cards as he wants. Eventually, he's going to run out. So D, the one that says that he can go from 0 to 11, is the most reasonable choice. Plus, if we looked at what that graph looks like in Desmos, 45 minus 4p. Oops, just kidding. 45 minus 4x, and we'll do 4x, not 4p. But I have this, right? So there's my graph. You can see that the money runs out at 11.25 packs of playing cards. Now, obviously, you can't buy 11.25 packs of playing cards. So he would be out of money by the time he hit 11 packs. So 11 is the limit or the boundary on what's possible there. So D is your best choice on that one. All right, that is the end of this lesson. Y'all have a beautiful day. Thank you.